All right, this is chapter 18. So the goal of this chapter is to sort of flesh out some ideas related to irreducible things related to irreducibility, which have come up in polynomials, but we'd like to generalize them a bit more and sort of dig into rings and look at some more of the rich structure that's going on inside them. So this section is on, this section is on irreducibles, associates, primes, and which I'm just going to call right now UFDs, which stands for unique factorization domains, which we'll get to at the end, and so on. So the intro is, so the goal here really is to look inside integral domains where there's a lot of variation, right? So is to investigate integral domains. So the reason for doing this is just sort of a broad look at things. Is we've kind of gone from rings in general to integral domains to fields. And in fields, generally lots of things happen. In integral domains, less things, and in rings in general, even less things. So what we'd like to look is in here, or maybe like even in here, is to sort of look at specific examples, look at what's going on. So to begin with, really the first three of these, the irreducibles, associates, and primes, will all get packaged together in here. So what I'm going to do for these is sort of introduce them all, give a couple of theorems that associated them, do a bunch of examples, and I'll do them in sort of in a slightly different order than I've listed them, because there's an order that makes sense. So we'll say, suppose, this almost goes without fail that when we talk about a D instead of a general R for a ring, that D will be an integral domain. So we'll say, suppose D is an integral domain, and A and B are in D. So then we say they're associates. We say that A and B are associates. So if there exists a unit, let's say exists a U, which is a unit in D such that A equals UB. So let me sort of give you a generalization, and then we're going to look at a more specific, not a generalization, but an example that'll really make it clear to you. So in Z is an integral domain. Think of an example like A equals 5 and B equals -5. These are associates because, let's say, 5 is -1 times -5, and this guy right here, -1, is a unit. So in a sense, we're kind of saying that they're similar to one another because they're different, or they're, I don't want to say quotient, but you can multiply one by a unit to get the other. So second example, which is sort of on the other end of the spectrum, is once you get to a field like Q, every two non-zero things are a unit. Let's say every non-zero pair are associates, rather. Right, for example, say 4 and, I don't know, 8/3. Right, those are associates because you can multiply 4 by something to get 8/3. Right, if you multiply it by 12/8, and 12/8, of course, is a unit because everything in Q which is not 0 is a unit. So you can always play this sort of game. And then between those two extremes, if you like, is something like in Z adjoined I. Right, remember, this is the ring of A plus BI. This is the imaginary I with A and B in the integers. So it's like a subset of the complex numbers. So these two guys, a equals -1 plus I, and b is 1 plus I, are associates because -1 plus I a is equal to I times 1 plus I, and I is a unit. Remember, everybody is a unit in its own place. Like back on the left, -1 is a unit in Z. Below that, 12/8 is a unit in Q. Up here, this is a unit in Z adjoint I. So in each case, these are associates. So second definition. So we'll say, suppose D is an integral domain. So I'm going to use this phrase a little bit, and we'll say, and A in D is the non-zero non-unit. So we're avoiding 0 and we're avoiding units. And we'll sort of see why in a second about, or we'll look at a familiar place where it'll make sense what that is. Right? So we'll say, then A is reducible in this case, if we may write A equals BC for B and C in D with B and C non-units. And then we can say, so the book doesn't use, I don't think the book uses the term reducible. They use the term irreducible and then not irreducible, which is a bit awkward. But we'll say then A is irreducible. Basically, if we cannot do this. In other words, if whenever A equals BC, that one of those two, A and B, must be a unit. So a place to think about this, interestingly, is what you think of as prime numbers in the integers in a normal number theoretic sense. So let me sort of give a few examples to clarify. So for example, in Z, so suppose that you didn't know the word prime. If you sort of flush that out of your head for a second, this will kind of make sense. So in Z, we could say A equals -6 is reducible because I can write -6 as a product of two things, and neither is a unit. But for example, still in Z, say A equals 7 is irreducible. Right, now at this point you might be like, well, that's because it's prime, but sort of again, throw the word prime out for a second and just sort of say to yourself, well, I cannot reduce it, right? Like, in other words, because if we put 7 equals BC, one of those must be a unit. Now, unlike in number theory we tend to avoid negative integers. But like in this case, we could do, say, 7 equals -1, -7, but -1 is a unit. So the way to think about this is, if I did this, I haven't really reduced it. Or I could do like 1 times 7, but that really doesn't count as far as reducing it is concerned. So reducing it sort of means, can you break it into things which are not units? And then we'll see more examples as we go. But just to contrast this, we'll say again, suppose D is an integral domain. Again, this is the definition. Over here, and A and D is a non-zero non-unit. So this is the sort of formal abstract algebra definition of prime. So, well, let me write it and then I'll make the comment I want to make. So A is prime if whenever A divides BC, then we must have A divides B or A divides C. So in a course like 406, in sort of a standard number theory course, this is a property of primeness, not a definition of primeness, but in abstract algebra it's a definition of primeness. So in number theory, this is a property of being prime. In number theory, the definition of being prime is more like being an irreducible. But here it's sort of slightly different because it corresponds more to the concept of a prime ideal, right? A prime ideal, remember, is if you have a product that's in the ideal, one of the two must be in the ideal. So that's sort of connected to the point of division, as we'll see more in this section. So it's sort of, you kind of have to tease those apart, especially if you're taking number theory right now, studying it right now. Keep in mind this may be out of alignment with what you're listening to and what you're learning in that course. So let me give a couple of examples. So a simple example, it'll sort of correspond to what we just said. In Z, A equals 6 is not prime. And the reason is, of course, is not because you can't factor it, right? Because we're taking a different approach here. It's because, or not because you can factor it, right? The approach here is like, well, I want to show that it's not prime. So it means I can show that it divides a product, neither of which of the things in the product does it divide. In other words, for example here, 6 divides, say, 3 times 4, but 6 does not divide 3, and 6 does not divide 4. So that's the reason why it's not prime in this case. So here's another example, and these can be pretty complicated when the rings get pretty complicated. So for example, suppose we look in Z adjoined root negative 3. So this is the ring consisting of let's say numbers of the form a plus b root 3 and root negative 3, with a and b being integers. So one thing to keep in mind is whenever we have things like this, you sort of have to recognize that they're rings. You could think about them as subrings of the complex numbers, but you shouldn't just sort of blindly only think about them as sets of elements, right? Like they're integral domains, they're rings, they have a multiplication, they have an addition, they have all that good stuff. So in this ring, the element 1 plus the square root of negative 3 is not prime. So to see this, it's not obvious, but I need to give a product that it divides where it doesn't divide either of the two, right? So in this case, to see this, observe that 1 plus the square root of negative 3 divides 4. So the reason, this is because 1 plus the square root of negative 3 times 1 minus the square root of negative 3, this is equal to 4 if you follow that out, right? Now, 4 is 2 times 2. So this tells us the 1 plus root negative 3 divides 2 times 2. But now I'm going to claim that it doesn't divide 2. And then that's good because there are 2 of these. But so 1 plus the square root of negative 3 does not divide 2. So then you might say, well, how do you know this? Like, how do you know there isn't something else that you can multiply 1 plus the square root of negative 3 by to get 2, given that things cancel out, right? So if it did, then there would exist a and b in the integers, such that 1 plus the square root of negative 3 times a plus b root negative 3 would be 2. Right? That's what it means for 1 plus root negative 3 to divide 2, right? There's something you can multiply by to get 2. So if you take this, I'm not going to go through the calculation, but give it a try. It's not hard. If you FOIL this out and solve for a and b, it's a system of equations. Right? They won't be in the integers. So in other words, you cannot find a, b in the integers that makes it work. So therefore we have this thing not dividing 2. So you might wonder at this point, we have these concepts of prime and irreducible, which seem very similar, at least. Like in integers, the notion of being irreducible is what we think of as being prime, and so you might be like, well, are irreducibles and primes the same thing, or are they different? And so there are 2 theorems that connect these two, the concepts of prime and irreducible. So I'm going to mention these 2 theorems and prove them, and then we'll sort of look at one last definition, and then we'll look at unique factorization domains. So the next two items, D and E in this case, are theorems that relate primes and irreducibles. So first fact, theorem. Turns out that if you're in an integral domain, then primes are irreducible. So in other words, in an integral domain, let's say it nicely, if A in D, an integral domain D, let's say if A is in D, if A and D is prime, then A is irreducible. So you cannot have prime but not irreducible. So the proof of both of the 2 theorems I'm going to give are fairly easy. So we'll go through this one first. So proof. Let's suppose A and D is prime. Claim it's irreducible. So how do we show something's irreducible? And the definition of irreducible is if you write it as a product, one of the 2 must be a unit. So let's say put A equal to BC. We claim one of BC is a unit. Now, of course, the fact that A equals BC means that it divides BC. All right, let me say this nicely. Since A equals BC, we know A divides BC. And here's where the primeness kicks in. Since A is prime, A divides B, or A divides C, or both, but it doesn't really matter. We know it divides one of them. So without loss of generality, let's say that A divides B. Suppose A divides B. So what this means is that B is a multiple of A. Let's say B is alpha A for some alpha in D. So now we have, take a look, we know that B is alpha A, but A is BC. This is alpha BC because A is BC. And now we're in integral domain. This is commutative, so I can move the B to the left if I want. We have a unity. Everything's pretty good in integral domain. So also in integral domain, we can cancel. So what I'm not doing is I'm not multiplying by a multiplicative inverse, right? We're not in a field. That's not guaranteed to exist, but we may cancel in an integral domain. So cancel that. So at this point, we know that C is a unit. And remember, that was the claim. We claimed that one of those is a unit. So in this, without loss of generality, C is a unit, QED. So this tells us, for example, that in an integral domain, like the integers, if you're prime, then you're irreducible. But the reverse is not so obvious, right? If irreducibility gave primeness, they'd be an if and only if we wouldn't use we wouldn't need 2 definitions. So it's likely that you can be irreducible but not prime. Right? But there may be situations under which if you are irreducible, you are prime, and that's what we want to give next. Right, so here's the sort of the theorem that goes with it. So the theorem says this: in a principal ideal domain, every irreducible is prime. So remember what a principal ideal domain is, if you've forgotten, right? So a principal ideal domain is, this sound redundant, but it'll sound like I'm not clarifying it, and then I'll clarify it. It's an integral domain in which every ideal is principal, right? So it is an integral domain in which every ideal has the form ideal generated by a single element. So the integers, for example, are a principal ideal domain. So in the integers we have prime if and only if irreducible. So let me sort of go through a quick proof of this, and then I can make a comment about the integers, and then we can look at an example where like we have like an irreducible which isn't prime. So here's the deal. We're going to start with an irreducible and show that it's prime. Suppose A in D is irreducible and A divides BC. So we claim A divides B or A divides C, right? That's what it takes to prove primality, right? So what we'll do is we'll define an ideal. Or rather, this is more like a I'll say it as defined because they did it in the notes. So I will be the ideal generated by two things, right? A and B, right? So remember that this definition is the set of AX plus BY, such as X and Y are in D. Right? So this ideal is generated by two elements, but because we're in a principal ideal, it must be generated by one element as well, right? So since D is a PID, we know there exists a D in big D such that we can write it just as the ideal generated by that, right? So we can write I equals the ideal generated by little d. Now, I know that A is in I, and I is generated by D. So this means that A is a multiple of D, right? Because remember the ideal generated by D is sort of all the multiples of D by things in the integral domain, right? So this tells us that A is D times alpha for some alpha in D, right? But now, what do we know? We know A is irreducible, which means one of these two things is a unit. Maybe both, but one of D, sorry, it's sort of sloppy. One of D and alpha is a unit. That's by the definition of A being irreducible, right? So look at the two possibilities. Right, so first look, if D is a unit, right, then look back at the ideal generated by D, right? Our capital I, the ideal is the ideal generated by the single element D. If D is a unit, that's everything, right? So then in this case, I is the ideal generated by D, which is the entire thing. So 1 is in D. But in this case, D is also or the ideal. Well, so I'm saying this badly. So if D is a unit, then the ideal I is which is the ideal generated by little d, is the entire thing. 1 is in D, so then 1 is in I, but I is also generated by A and B. This tells us that 1 must be a linear combination of these two, right? So 1 is AX plus BY, let me clean this up, AX plus BY for some X and Y in D. So if we take this thing and multiply by C, I'm going to put the C right there. So if we look at that product, right, we know that A divides ACX, and we know that A divides BC, So this tells us that A must divide C. All right, so in other words, since A divides ACX and A divides BCY, we have A divides C. Right? Now, just to clarify, we're halfway done because we just did one bullet. But just to clarify, this is because A divides BC, and that's by assumption up here. So this is the case if D is a unit. So what if D is not the one that's the unit? So the other bullet point is much easier, right? So remember, here was the case, this is the case where alpha is a unit. So if alpha is a unit, then since A is D times alpha, the ideal generated by A is the same as the ideal generated by D, which is I. Now, since B is an I, we know that B is a multiple of A. We could say B is A beta for some beta in D. But then we know that A divides B, and that's the end. Now, one thing I just want to point out before we make a couple comments and move on is this point up here. Right, it's worth taking a look. This idea about what ideals look like when the generators have different forms, like if the generator of an ideal is a unit, if an ideal contains one, if, like in this case, if alpha is a unit, what we're saying here is that A and D are associates, and then what we're concluding is that the ideal generated by A and the ideal generated by D are, you know, identical. And so that may not be obvious to you, right? Like you might, like it's a quick proof, which is why I'm not including it, but it may not be screamingly obvious. So it's worth looking at sort of these kinds of little minor points about why this is the case, right? So it's worth investigating that. It's like, it's one of these things that's not difficult, but if it's not clear, it's just you sort of may not have straightened those things out in your head, you know, right away. So in any case, there's this big thus that concludes in it. Right? In a case like Z, which is a PID, so, you know, take a second to ask yourself why. That takes a little bit of work, but you know, it's not bad to show. Irreducibles are the same as primes. But if we're not in a PID, then we can have an irreducible which isn't prime. So I want to give an example of one of these. Before I do, I need to sort of define something additional, which is like a helper function. So to see, because this actually gets really tricky, digging into these really deeply and proving whether things are irreducible and prime can be a lot of work. They sound like really simple terms, but they're not at all simple terms when the rings get complicated. So be aware that like a statement like prove that this is prime might sound really like it should be easy, but by no means is it, right? Or saying something's irreducible, by no means should it be obvious. So the example I'm going to give this auxiliary definition. That'll help us see. So to see an example, the following can help. So I'll give this as F. So definition. So specifically, I'm going to look at a specific type of integral domain. So that that lowercase d and z with d let's say with d being square free. Or actually, let me be cautious. Let's say d is not 1 and d is square free. So this means not divisible by any square. In other words, by any perfect square. So for example, I couldn't have 8. Basically, I'm about to take the square root of d, and I don't want to be able to pull things out. So say 5 is fine, 10 is fine, because even though I can factor 10, I can't divide it by a perfect square. So in the integral domain given by z adjoin the square root of d, we define the norm. So n a plus b root d as the absolute value of a squared minus db squared. So it turns out that the following is true. So the following are obvious. I'm not going to prove these. They're pretty easy. Not obvious. That's a terrible word. Are easy to show. So the norm has the following properties: is that if you take the norm and you get 0, this is if and only if x is 0. So x is anything of the form a plus b root d, right? X and y in this case. Turns out that n of xy is n of x, n of y. These are mostly shown just by brute force. So they're not tricky, there's nothing sneaky about them. And that n of x is 1. I think the book relegates them to an exercise, but you can check that. If and only if x is a unit. So I would say give these a proof if you give these a go at proving them if you want to. Right? But the only reason I want to give these is to sort of give an example. So in z joined root -3, this element 1 plus the square root of -3 is irreducible. Now, if that looks familiar, earlier on in this video, we showed this guy is not prime. Right, so what we're really showing here is we're giving an example of an irreducible which isn't prime. Right? So to show that it's irreducible, so there's a little proof that's in here. Right? So assume that 1 plus root -3, assume that I multiply it with neither being a unit. So this is really by contradiction. Right. So if I take the norm of both sides, I get the norm. Let me do it this way. We'll say the norm of x times the norm of y is the norm of xy, which is the norm of 1 plus root -3. Now, if we look at the definition of the norm function, this is the absolute value of a squared, which is 1 minus d, but d is -3. So in this case, we have plus 3, and this is 4. Now, if you look at this, the norm itself is a positive integer, right? Because we're taking the absolute value, and the norm is because it's an integer, if I have norm of x times norm of y to be 4, and they're not units, right? And we said that the norm is 1 if and only if it's a unit, right? So since x and y are not units, both of the norms must be 2, right? So we must have norm of x equals norm of y equals 2, because the only way I can multiply them and get 4, right? But if you try this, if we solve the norm, like so, in other words, if I take a random element, let's say a plus b root -3, and set it equal to 2, we get the absolute value of a squared plus 3b squared equals 2. Or if you prefer, since that's already positive, I can ditch the absolute value. I get this, which is impossible. So it's like a mini QED there. Now, just as to why it's impossible, the reason is because a and b are integers, right? So as soon as, like, if a and b are both 0, I get 0. And as soon as one of them is 1 or -1, it's already too big. So I can never get 2 from a and b being integers. Right? So the practical upshot, I don't want to erase the screen right here, so I'll just put this in right here, is that, like for this example, is that I know that this guy is not a PID. Right? Because we've given an example of an irreducible which isn't prime. So, there's one more thing I want to cover in this chapter, which is the definition of a unique factorization domain. So the reason I want to give this is because it's related, sort of in number theory, to the concept of factoring into, like in number theory, you factor things into the product of primes. And so this is sort of a generalization of that. So it's a quick topic just at the end of this section. So what I'll do is here, I'll clear the screen off, and then I'll give the definition and an example and a couple of theorems, but I'm not really gonna, one theorem I won't prove because it's long, the other one I'll prove, but it takes about 10 seconds. So let me clear this all off and we'll go through that. So this is 3. This is on unique factorization domains. So let me do this. Let me give the definition, and then I'll sort of give a prototypical example. So an integral domain D is a UFD, so unique factorization domain, if every non-zero, non-unit can be written as a product of irreducibles in D. And the factorization, or the product if you like, is let's say is up to, or is unique, I guess is maybe the more official way, to order and associates. So that's a bit unclear. Let me look at the prototype example. Here's the integers. So prototypical example is Z, right? So if you take a number in Z, and you can factor it, right? So take, for example, the one I did in the notes is 315. And so 315, if we factor this as primes, like pretend we're in number theory, we factor this as primes, right? And we look at these, and we go, these are all irreducible, because that's the same as prime in Z, right? These are 3, 5, and 7 are irreducible in Z, aka prime in Z. Now, this isn't, of course, the only possibility. If I have negative integers, right, we can also do 3, 1, 5 equals -3, 3, -5, 7. But I don't count that as different because I swapped out, say, 3 with -3, right? I swapped it out with an associate. This does not count as different, because say -3 and 3 are associates. 5 and negative 5, or negative 5 and 5 are associates. Right. Now, you could also say, hey, look, I'm going to give a different factorization. I'm going to say 315 is 3 times 3 times 5 times 7 times 1 times negative 1 times negative 1. But we don't count that either. Right? It doesn't count as different. Right? Because all I did was stick some units on here. Right? And that's sort of, it's kind of like cheating, right? So a unique factorization domain is a place where that I can only do this once, right? So there's no other way to break down 315, right? I can't write it as like 11 times 13 or something like that. Like I cannot use different primes to do it. Right? So an example, let me give you an example of one that isn't. So z adjoined the square root of negative 5. And these can be hard, right? This is not an easy example, but this is sort of the easy example. I'm not going to work through the details because the details are sort of interesting to do as exercises. This is not a UFD. Right? So to see this, 6 is equal to 2 times 3. 6 is also equal to 1 plus root negative 5, 1 minus root negative 5. So now the statement I'm about to make is not at all screamingly obvious. So, but I'll make it anyway because we sort of have to appreciate what we've done when we do this, right? So we need to prove a few things, right? So I'll say show, and so give it a try, is that all of these four are irreducible. That's not hard. You can use the norm for that. You can use, in the first example, well actually let's be cautious, we could use the norm for these. This aren't so bad. But we also need to show, this isn't enough. We need to show that these are not like pairs by associates, right? So back on the other side, we could look at this and we could be like, hey look, when I change this to this guy, 3 to negative 3, that's just an associate. So it doesn't really count as changing it. So over on the right hand side, you could say, well, maybe 2 and 1 plus root negative 5 are associates. And so I've swapped out 2 for something that's associate, and maybe 3 is the associate of 1 minus root negative 5. So we have to show that this is not true either, right? So that 2 and 3 are not associates of 1 plus root negative 5, 1 minus root negative 5. We could do this by showing that if you multiply, you could say like, what do the units look like in this? Like, what do the units in z root negative 5 look like? If you wanted to multiply 2 by a unit and get 1 plus the square root of negative 5, like, could you do it, right? Like, why could you not do it? So just to clarify, these are not obvious, right? Like, this is a decent amount of work in itself. But worth trying, right? Like any one of these is like a good question. It's like a good homework question or even a reasonable exam question, is to work through the details, which is why I'm avoiding it right now. I'm just sort of moving it back to a place where we can understand what we need to do. So 2 closing theorems here. So the first one I'm not going to prove because it's long, but is a principal ideal domain is a unique factorization domain. So the proof of that is lengthy. So what that says, for example, is that z adjoin the square root of negative 5, since it's not a UFD, cannot be a PID either, because PID must be a UFD, right? Principal ideal domain must be a unique factorization domain. And the corollary for this is that if F is a field, then Fx is a UFD. Proof of this, once we have the theorem, is easy. The proof is we proved that Fx is a PID. And then apply the theorem. QED. So just to end with an example, which I'll put down here, is you could say something like R rejoined X. This is the ring of polynomials that you know and love from pre-calculus, right? Regular old standard polynomials. This is the unique factorization domain. And this should be sensible to you. If you factor a polynomial, when you factor a polynomial as far as you can, like you get a factorization, you get some polynomials that you can't factor any further, and the ones that you get are irreducible, like they don't go further, and there's no other sneaky way to factor that you didn't get, right? There's no up to associates going on, or putting in units doesn't count, things like that. So this should make good sense in this particular example. So that is the end of that section.